Yeah, thanks, Anna, and thanks the organizers for the invitation. Yeah, I would have loved really to come to LA, and I really miss seeing you and have real discussions, but I'm happy that it's also working this way, and the pandemic is not coming maybe 10 years earlier, before the times of Zoom. So yeah, I'd like to present a result on the rates of enhanced dissipation. So the setting that I'm considering is a fluid that is mixed by fluid flow.
Christian, would it be possible for you to, we cannot see you, I guess, because you're using your tablet. So there was
I will spotlight his video.
Okay. Sorry to interrupt you. Go ahead.
Yeah, I'm sorry.
Great. We can see you. Yep. Perfect.
Okay. Sorry for this. Okay, so I'm considering a quantity, a diffusive quantity that is being mixed by a flow. And in this situation, there are principally two ways to mix. So the one is by advection. So advection means, I draw a little picture here. Suppose we have some paint or black and white color, and we want to mix it, and then we apply some fluid flow, which I indicated here with the red arrows. Then after a certain time, we have a certain filamentation. So if we wait a little bit, then the filamentation is on a quite coarse scale. But if I continue and I refine possibly my flow, then the filamentation is getting finer and finer. So this is the effect of advection, the effect of a fluid flow. The other possibility that I allow here in this model is mixing by diffusion. So while advection acts on the scales by creating filaments, diffusion acts on the intensity, or maybe even better on the gradients of intensity. So, for instance, if I have a configuration which has a very very pointed intensity somewhere, then the diffusion will act in a way that it smooths out this sharp gradient. So mathematically, the situation is quite simple. It's described by a linear advection-diffusion equation. For simplicity, I'd like to consider the torus. And here theta is a passive scalar. The passive scalar means that the velocity u has no feedback on theta itself. So theta is completely thought to be completely independent of u. And so typically, typical scenarios would be like ink in water, salt, or maybe also in some situation, temperature, concentration of something. The velocity field should be divergence-free, as we consider most of the times, at least I guess in this workshop. And kappa is the diffusivity constant. It's positive, but we assume that it's small. Yeah? So in this non-dimensionalized setting, it's something like the inverse Becquerel number. And under these assumptions, so periodicity, divergence-free velocity, theta is certainly preserved in time, or the average of theta is preserved in time, and we assume also for simplicity that it's zero initially, and therefore zero for all times. Yeah, that means if I think of this black-white mixture and assigns, for instance, here the black part a value +1, the white part the value -1, then then my model should be covered half by black and half by white ink or whatever it is, paint. So let me start with some very oversimplified heuristics. This is the way I used to think about the interaction between diffusion and advection. And for this, I'd like to consider a configuration which is initially very regular. So the variations are all of order 1 for simplicity, but that is really not at all important here. Let's suppose theta really takes values between -1 and 1. Its L2 norm or any other LP norm that you prefer is of order 1, but also the gradient or the norm of the gradient is of order 1. Yeah, so in this way, the typical interface between one phase, the +1 phase, and the -1 phase is of order 1. Yeah. And then let's suppose we apply a regular straightening flow, by which I mean also that the enstrophy, so the L2 norm of the velocity gradient is order 1. No? I call it U. It's some quantity which is independent certainly of kappa. Shouldn't be too large, shouldn't be too small. But since kappa is smaller compared to 1, so this gradient is certainly much larger than the diffusivity constant. So what is happening now? So suppose we have this flow, and we have a filamentation, and we have diffusion on the same time. So since the interfacial width here is of order 1, what is happening at the first place is that the filamentation or mixing by filamentation is much more effective than by diffusion. So the way I think of it is that diffusion, well, of course, diffusion happens in the beginning, but it's not as important. So initially we have a filamentation. The filaments are quite thick or are getting thinner in time, of course. But in the beginning, really, I think of having essentially advection. And then at a later time, when the filaments are getting thinner and thinner, diffusion kicks in more and more. And at a certain, then there will be a moment when everything I stir, so every filament I'm creating will be diffused immediately. So therefore, the way I think of it is just now in this oversimplified heuristic that at a later time, we only have diffusion. So let's consider first the early advection dominating mixing state, and let's suppose really that kappa is 0, so that we have no diffusion at all initially. Then it's clear that the intensity, so the L2 integral here, is preserved in time. And what we expect is, if we have really a mixing flow, is that the H-1 norm of theta or any other negative Sobolev norm, or some guys of I like to consider optimal transportation norms, which are also related to negative Sobolev norms. All these guys should somehow decrease, and what can be shown that is they cannot decrease faster than exponentially in time. Yeah, the first lower bound goes back to this work of Crippa and Delelis, which Gianluca just mentioned, and then there has been a follow-up work. So the Crippa Delelis derived a lower bound for certain Lagrangian mixing measures, and then there has been a couple of papers proving lower bounds also in the Eulerian case. And in fact, these bounds are sharp, and this is why I wrote here twiddle. There are also upper bound constructions which satisfy this bound by Alberti, Crippa, Mazzucato, Jaus, Latosch, Elgindis, Latosch, and recently also using a stochastic approach by Blumenthal, Woodrosian, Pochon, Smith. So this is the advective case, and now as I just said, I expect that at late times diffusion is the dominant mechanism, and therefore, just for simplicity, I assume that U is 0, so there's no advection at all. If there's no advection at all, I can solve the heat equation scale-wise, just going to the Fourier space, and then I have an ODE in Fourier space, and it is solved, and it can be solved for every wave number, and what you see is that the every mode is decreasing exponentially in time. and the exponential rate is proportional to kappa and the square of the wave number. And if you now suppose that there's essentially only one wave number or one dominant wave number in your setting, then this is also the one at which the full L2 norm is decreasing. Yeah. So if there's only essentially one wave number present, then the whole L2 norm decreases at a rate which is determined by this wave number. So the question here is now in this heuristics, what is the wave number that appears when we have this interplay of advection and diffusion? Yeah, and this wave number is exactly determined by the balance between advection and diffusion. So I made another cartoon here. So let's suppose again, the mixture looked like this in the beginning. So this is the initial configuration. I assume a smooth interface, but that is not as important here. Then we have essentially a fluid flow. The fluid flow creates a filamentation up to some transition or crossover time, which I call TB. So B will stand for balance at this moment, but later also for bachelor. And then at a later time, so if for times much larger than this crossover time, we have essentially diffusion. Yeah, so therefore we have this grayish picture. Then I can apply some dimensional analysis and just figure out at which scale the advection and the diffusion term balance in the advection-diffusion equation. And so this happens exactly at the wave number square root u over kappa. So you remember u was just the constant in time L2 norm of the velocity gradient. And as many of you will know, the inverse of this wave number, it's a length scale, and this is just the bachelor scale. Yeah, and the bachelor scale is exactly defined in this way. The bachelor scale is the scale at which advection diffusion are in balance. So therefore, if I just said in the previous slide, if there's a dominant wave number KB, then the L2 norm should decrease exactly at this rate. Now, if KB is proportional to 1 over square root kappa, you see that the exponential rate should be independent of kappa, at least on this very coarse heuristic level. Yeah. So therefore, we might maybe expect that the L2 norm at late times decreases as some exponential e to the minus dt for some d of order 1. And in fact, this phenomenon is called an enhanced dissipation. So just recall d equal to kappa is just the case that we have for the regular heat equation. And that means the fluid flow that I apply here increases the exponential rate from kappa to 1. So we have a much, much faster dissipation in this, at least, Gedankenexperiment. So what about rigorous results? What is known? So let me just introduce a definition with which I will work here. So I say that the flow is dissipation enhancement, or that we have the phenomenon of dissipation enhancement if there exists this rate d, which should be much larger than kappa, and maybe some quantity, some constant lambda, which should be bigger than 1, so that the L2 norm decreases with this rate. So lambda times e to the minus dt. The first results have been quantitatively. There's this groundbreaking paper by Konstantin Kiselev and Zlatosh, who derived a sharp characterization of steady velocity fields in which we have the phenomenon of enhanced dissipation. And then in recent years, there has been quite a couple of works on quantitative results, most of them for shear flows. And the shear flow estimates are as follows. So this quantity lambda is order 1, and d, this rate in the exponential is just some power of the diffusivity constant for alpha between 0 and 1. So for monotone shear flows without boundary, I guess alpha is a third, and there are various results with boundary, without boundary, non-monotone, and so on. So there, I guess the name here is, which has to be mentioned, is Michele Cottisilati, and then there are many works with Bedrosian, Drivas, Colombo, Wittmeier, Dolce. And there's also a paper by Wei who considers shear flows. So the other one, the other result I'm aware of is for also by this group, Bedrosian, Blumenthal, Pujon, Smith, is for randomly forced fluid systems. So these are Navier-Stokes equations with a random forcing, for instance, in 2D, or Stokes equations in any dimensions with a random forcing. And in this case, they are able to show two results. So the first result they show is that they have uniform exponential decay rates. So D is order 1. But then there's a prefactor of the order 1 over kappa. And they also conclude that one could derive another bound which has a prefactor of order 1, so independent of kappa, and D is increasing logarithmically with 1 over log 1 over kappa. So these are examples for these enhanced dissipation rates, and the question is, what is the best rate that you can get under quite general assumptions? And the assumptions I'm imposing here are the following. So as I said earlier, I'm supposing that my initial configuration is order 1 in intensity, and also is regular, so that the gradient of theta naught is also order 1. And I have no assumptions on the velocity field apart from U being divergence free. And I'm imposing an integral bound on the velocity gradient in this way. The reason why I'm imposing this bound is because this group, Bedrosian, Blumenthal, Pujon, Smith, have similar estimates on the velocity field. They are a little bit weaker than what we often consider, namely fixed enstrophy bounds. So therefore, this situation here is a little bit more general, but we can think in most of the times of having bounds of this form, and I will essentially also only discuss the case alpha equal to 1. So the test case is the case that I would say we understand best is the case alpha is 1, and the enstrophy is just fixed in time. So in this case, the result is the following. So suppose we have a flow which generates dissipation enhancement in the sense that there exists a lambda and a quantity d, so that this formula holds. Then we have the following upper bound on d or lower bound on lambda, which depend on each other. So let's see what we have. So first of all, this is still a modest result because it assumes that we have enhanced dissipation, and then figures out what would be a suitable bound on the on the rate or on the prefactor, but it's still a first result, in I would say in the right direction. Let's discuss the pivotal cases. So if lambda is one, you see that we have an upper bound on d in the form 1 over log 1 over kappa. Yeah, which means that if there's no prefactor here, then we cannot expect that we have an exponential decay rate that is independent of the diffusivity constant. And on the other hand, if we expect that this constant d is really order 1, then we have to have a prefactorial here, lambda, that increases with when kappa is decreasing, namely logarithmically. So the first result, if we allow, if we say we do not allow for a prefactor, so if we say lambda is 1, then we get this this bound on the exponential rate, and by this work by Bedrosian and co-workers, this is in fact sharp. Yeah, and on the other hand, if d is if we are looking for exponential rates which are uniform in the diffusivity constant, we get a lower bound on the prefactor, and it is not clear whether this is optimal or not, because the only result I'm aware of is this also in the stochastic setting, and there lambda is 1 over kappa. So there have been simultaneously results. They are not optimal, so a little bit weaker by Breuer and Nguyen, having this more or less the same statement. And there's also a result which is also very interesting by Michele Cottiselati, Delgadino, and Elgindi. And this shows the following: if there is a universal mixer, the universal mixer is a velocity field which mixes every initial datum. If there's a universal mixer which is Lipschitz with a bound Lipschitz constant, then we have enhanced dissipation with lambda of order 1, and a lower bound on the exponential rate is given by log to the -2 1 over kappa. So they differ. The results here differ only by a power on the logarithm. So also this result is almost sharp.
So Christian, 2 more minutes, 2-3 minutes.
Yeah, thanks. Okay, so this result is almost what I want to say is this result is different from a result that I would love to have, namely a lower bound on the L2 norm in this form. But this is certainly also controversial. I think there are people who believe that such bounds will not be true in general. I do not have really an opinion or a straight. I don't really know what I expect here in this case. Another comment that I'd like to make is that the assumption that the velocity, that the initial configuration is regular in this sense, is necessary. Otherwise, we could, for every given exponential decay rate, we could find an initial datum so that we have an exponential, arbitrary fast exponential rate of decay. Okay, so the result relies on some stability estimates for advection-diffusion equation using optimal transportation techniques. I will skip this point. I just like to, because I announced it in the title that I submitted, I just like to make a remark on a related result on mixing. And that can be deduced just by an interpolation argument combined with the previous result on the enhanced dissipation. And I'm just displaying it for the case alpha equal to 1, which is just, for instance, the case if gradient u is fixed, or its 2 norm is fixed over time. then the result would show that supposing that the h-1 norm is decaying exponentially in time with some rate d and a certain prefactor, which I will discuss in a second, then we have the same bound on the dissipation on the dissipation rate that we had that I assumed before. And the only thing that I want to remark here is that this is not a random prefactor, but it's just a logarithmic correction of the Batchelor scale. Yeah. So the Batchelor scale, we know the Batchelor length scale is just kappa or order kappa. So the prefactor that we have here is just the Batchelor scale, and that makes sense, I would say, because for large times that should be valid for very large times. For large times, I expect that we have advection in the beginning, and then at a later stage the diffusive regime comes in, and this is exactly when the typical length scale is of the order of the Batchelor scale, and therefore we have this here as a prefactor. So this is not surprising, I guess. Yeah, with this I'm done, and I thank you for your attention.